Hello, and welcome to a presentation on EvoDev, an implementation and interactive interface for evolutionary algorithms. So what are evolutionary algorithms? Well, they are a subfield of artificial intelligence inspired by the natural processes of evolution. These ideas range from population-based approaches such as natural selection to genetic concepts such as mutation and crossover. In a genetic algorithm, a population of candidate solutions to a given problem are randomly generated in one of several encodings, which efficiently represent solutions. After population initialization, these solutions are repeatedly selected, combined, and mutated, such that over thousands of generations, the population converges to the solution. Genetic algorithms can be creatively configured to solve problems in computer science that are challenging for conventional approaches.
However, evolutionary algorithms are often overlooked as candidate algorithms for practical and research-based problems. We believe that this is largely because the fundamental ideas behind these algorithms are not as widely studied and understood in the field of computer science. However, these algorithms are rather simple and intuitive at their core. While there exist tools and libraries for implementing genetic algorithms, we believe that there is a lack of simple and accessible learning tools for users to familiarize themselves with their concepts. For this reason, we have developed EvoDev. Our goal is to encourage users with limited knowledge of genetic algorithms to experiment and learn in a simple, accessible interface. This will enable users to familiarize themselves with the construction of these algorithms, the relationships between parameters, and a wide variety of potential applications.
We developed this program for use in the Jupyter Notebook environment, commonly used in data science applications. By utilizing the Plotly Jupyter Dash library, we were able to integrate a real-time interactive dashboard. The dashboard allows for user-customizable problem definitions, solution representations, as well as solution selection, mutation, and recombination techniques. Using this framework, users are able to experiment with the configuration of their algorithm, visualize the evolutionary process as the population learns to solve the problem, and pause the algorithm in real time in order to update the parameters. To help the user get started with our application, we implemented 4 predefined problem instances and configurations: the Western Sahara TSP, the knapsack problem, a 10 by 10 Sudoku board, and the 64 queens problem.
In Figure 2, you can see an example workflow of the application using the Western Sahara traveling salesman problem. The general traveling salesman problem is thus: given a list of cities and the distances between each pair, find the shortest possible route that visits each city and returns to the original one. The Western Sahara version of this problem involves the real-life example of 29 cities in the Western Sahara. This is a difficult and important problem in computer science, as many other problems can be generalized to a version of this one. There are many different ways to solve this problem, but many of them are computationally expensive, taking either a large amount of space or a lot of time. Here we solve this problem using a genetic algorithm in order to demonstrate their power and versatility.
More advanced users also have the option of defining their own custom problem and implementing a custom visualization for the main app to display. By using this feature, a user will be able to gain a better understanding of the underlying processes involved in their algorithm and leverage this tool for the problems they're currently working on.
Once the user has defined a problem, they proceed by running the main app. Here they will be prompted to define further algorithm parameters. Once the user runs the algorithm by clicking Start, the results will update dynamically to inform of the success of the population. We implement several common visualizations used by evolutionary computing practitioners: the convergence of minimum, maximum, and mean population fitness, a heat map displaying population diversity, and a custom visualization to display the decoded solution representation, which in the case of the traveling salesman problem, is a graph network depicting the route around the nodes. As you can see, the user has the ability to pause the algorithm and dynamically change certain parameters. This way, a user can begin to understand the relationship between the initial parameters of the algorithm and the way in which it runs. Once a user is satisfied with their experiment, they can terminate the algorithm and export the population of final solutions for further analysis.
The goal of EvoDev was to facilitate understanding and experimentation with genetic algorithms by emphasizing their simplicity, versatility, and natural intuition. In order to accomplish this, we created a low-code application that encourages users to engage with genetic algorithms in a novel, fun, and interactive way. We hope that this tool will help increase interest in genetic algorithms and that more people will be inspired to integrate genetic algorithms into their work.